Hello grade 7, welcome to your Unit 11 review. I made this review based on your suggestions from the survey I did yesterday. So I'm hoping to touch on every concept in the unit, and then I'm going to try and also just point out a few different examples of permutations or combinations or the fundamental counting principle. And then your test will be largely based off of these types of questions. Of course, there'll be some that are different, because I want to see if you can apply the ideas, but I'm not going to put any really tricky or really hard questions on the test for Friday. So the fundamental counting principle, we often use it when we're talking about making different combinations and groups of things, where we're pulling things from different areas. So often we use it when we're talking about making ice cream sundaes. Let's say I have 3 flavors of ice cream, 2 types of sprinkles, and 2 types of sauces. How many different combinations could I make for my ice cream? So I could pull 1 flavor, 1 sprinkle, 1 sauce. We also talk about the fundamental counting principle when we're dealing with things like I'm going to a fancy restaurant and I can pick what I would like to drink, what kind of salad I want, what kind of meat I want, what kind of side I want, and then what kind of dessert I want. How many different combinations of meals can I use? So here's another example that we're going to do. Let's say you're getting dressed in the morning and you look in your closet and you have 4 shirts, 5 pants, and 3 shoes. How many different combinations could you make? Well, in theory, if I wanted to, I could line up my 4 shirts, 1, 2, 3, 4. And then I could think from those 4 shirts, I have 1, 2, 3, 4, 5 pant options, and then 1, 2, 3 shoe options. At the end of each tree diagram is a different arrangement or combination. That would work, but it would take a long time. So that's where the fundamental counting principle comes in, where you just multiply all the different options that you have to get all the different arrangements. So 4 times 5 is 20, and 20 times 3 is 60. So on the test, when you're going to use the fundamental counting principle, look for things like combinations of shirts, pants, shoes. You could look for combinations of ice cream sundaes or different meals, things like that, where you're pulling something from each category to make a different combination. Then we have permutations. Now, the main thing to remember with permutation is that the order matters. So order matters when I'm talking about a bike lock, right? Let's say my bike lock code is 1, 2, 3, 4. If you put 2, 3, 1, 4 in, it will not unlock your bike. So order matters with permutation. Now, sometimes we use the fundamental counting principle when we figure out permutations, and then sometimes we use factorials. So basically how you decide which one you should use is you need to think factorials I use when I've used up an option. So let's take a look at this question here. I have a bike lock with 4 different slots, and each slot can have any one of the digits from 0 to 9. And then it tells me the digits can repeat. So that means if I wanted, my bike lock could be 0, 0, 0, 0, or 1, 1, 2, 2, where the digits repeat. So what I like to do when I think about permutations, and I think about bike locks, I think about 4 different blanks, 1, 2, 3, 4. And I think, okay, in my first blank, how many different options do I have there? Well, I have 10 different options. In my second blank, how many options for digits do I have? Well, I still have 10, right? Because I have 1 through 9 and then 0. Because the digits can repeat. So if I put, for example, as my first one, let's say I put the number 1 in, that doesn't mean that I can't have number 1 here. So I still have 10 choices. So I do 10, and then 10 choices for the second blank, 10 for the third, and then 10 for the fourth. So that means I can do 10 times 10 times 10 times 10, and I will discover that I have 10,000 different options for my bike lock with the digits not repeating, which is why locks work, right? If you think about it, if somebody wants to take your bike and doesn't know the code, they would have to try up to 10,000 different combinations or arrangements in order to figure out what your bike lock is. So this was actually a case where I used the fundamental counting principle because I multiplied by, you could think of it as options for each blank was 10, 10, and 10. But now let's look at it a little bit differently where it's still a permutation, but there's something different. So it's the same question up till the end. Bike lock with 4 different slots, any one of the digits from 0 to 9. But then it tells me the digits cannot repeat. So it's still a permutation and order matters, but I can't use a fundamental counting principle. So instead I have to think about it like this. I still have 4 blanks. How many choices do I have for the 4 blanks? Well, I have 10. But let's say I put the digit 1 here. That means all my remaining ones cannot have a 1 in it. So that means for my second blank, I only have 9 digits as an option. So let's say I put the number 4 there. That means for my third blank, I can't use 1 or 4, so I only have 8 options left. And then I only have 7 options. And then I can multiply those out, and I would get, I'm not going to do it for you, but I would get a number that's smaller than 10,000. So this is still a permutation because order still matters, but I'm using more of the factorial style where my numbers go down each time because I've used up one of my options. So permutations, you think a lot about. Bike locks will be your most normal example of a permutation. All right, let's look at a combination. So a combination is when order doesn't matter. So for example, I'm making a pizza. Let's say I have 8 different toppings, but I'm only allowed to put 3 on my pizza. So remember, if I were to put ham, pineapple, and bacon on my pizza, it's the same as me putting bacon, ham, and pineapple on my pizza. The order doesn't change. I still have a pizza with those 3 toppings on it. So the order doesn't matter. Same with if I were to pick, let's say I have 10 friends. I'm going to pick 3 of them to come with me to a concert. I can only pick 3 of them. The order doesn't matter. If I pick Bob, Alice, and Carl, that's the same as me taking Carl, Alice, and Bob. So combination order does not matter. I know the trickiest part is to figure out if something's a permutation or combination. So you just have to sit and think about it for a little bit on your test. Does the order matter or not? So in order for us to solve this one, what I need to do first is I need to think, well, let's pretend the order doesn't matter. And we can always still think of our 3 blanks. For my first topping choice, how many toppings can I choose from? Well, I can choose from 8 different toppings. So let's say I decide I'm going to put ham on. That means for my second choice, I only have 7 toppings to choose from and then 6. So notice grade 7, I have 3 blanks because I can put 3 toppings on my pizza, but I start with the number 8 because that's how many options I have to start with. So then I would do 8 times 7 times 6. But now, because it's a combination, I need to divide this whole thing. So I'm going to make it a fraction because I want to get rid of those combinations that repeat themselves. Like I said, ham, pineapple, bacon is the same as bacon, pineapple, ham. So the way I decide what to divide by is I think, well, how many blanks did I have? I had 3 blanks. So I'm going to divide by 3 factorial. Which you should remember that 3 factorial is 3 times 2 times 1. Because that gets rid of all the doubles. So I would do 8 times 7 times 6 divided by 3 times 2 times 1. And then I would get my answer. That's how it works with combinations. So let's say I had a pizza. Let's do it one more time. Let's just change it up a little bit. Erase that just so you can see where the numbers come from. Now, let's say I had a pizza with 20 different toppings, but I can only put 5 on my pizza. I would start with, I can put 5, so I have 5 blanks, but then I have 20 to choose from, then 19, then 18, then 17, then 16. They all multiply. And then I divide by, well, I had 5 choices, I have 5 blanks, 5 factorial. Okay? All right. Let's just look at 2 more. We're not going to actually calculate it, but let's just decide if it's a permutation or a combination. So we have 27 students in grade 7. 3 of them will be class reps. How many different arrangements can you have? Is this going to be a permutation or a combination? So if I have 3 people representing my class, maybe they're the representatives that get to talk to the principal about ideas for our school. In this case, it's going to be a combination because the order doesn't matter. If I pick, let's say, Nolan, Hannah, and Nathan to be the reps for grade 7, it's the same as me picking Nathan, Nolan, and Hannah. It doesn't change. So the combination, I'm finding a combination, not a permutation. But if I now want to elect people in our class, and I have a president, a secretary, and a treasurer, those are different positions. So then it's a permutation because the order matters. So let's say I have Nolan be the president, and then I have Hannah be the secretary and Nathan the treasurer. That's different than if Hannah were the president, Nathan the secretary, and Nolan the treasurer. So then it's a permutation because the order or what position they have does matter. Okay, now let's go on to our spinners. We're going to talk a little bit about things being mutually exclusive and when to add things. So let's take a look at this spinner and let's figure out the probability that I would land on yellow. So I noticed that there are 8 different slots. 2 out of 8 are yellow, which I can simplify. The probability that I land on yellow is 1 out of 4. The probability that I land on red is 1 out of 8. Now, if I want to figure out the probability of yellow or red, when you see or, typically that means we're going to add. That means I'm going to spin the spinner, and let's say I'm going to win a prize if I land on yellow or red. I don't need to land on both of them, just one or the other. So that means if I wanted, let's switch back to this. If I wanted, I could look at, well, there's 2 yellows and 1 red. My answer's 3 out of 8. Or I could have added my probability for yellow with my probability for 8. And I would get 3 out of 8. Okay, so when you see or, we're typically going to add if the events are mutually exclusive. And that means mutually exclusive means they cannot happen at the same time. So if I look at my spinner, it cannot happen at the same time that I land on yellow and red. They're mutually exclusive. So I can just add up those 2 probabilities. Same with the probability of red, 1 out of 8, and the probability of even, which is 4 out of 8. The probability that I land on red or even, remember it's or, that's important, one or the other. I can add up the 2 different probabilities. Oopsies. And I get 5/8. Okay. So you could think about maybe you're playing a game at the bazaar and you have to spin the spinner and you're told you'll get a prize if you land on a red or an even. You have a pretty good chance, 5 out of 8, of getting a prize, which is better than just saying you only get a prize if you land on red. It's kind of like the cakewalk, if you think about at the bazaar, right? You get a prize if they pull your number. In that case, it's just one choice. Maybe they said, well, if I pull number 2, and there's like 20, I don't know how many kids walk on the cakewalk, 15 kids, you only have one chance to win the cakewalk. But maybe they said, oh, this time we're actually going to pull out 5 different numbers and 5 people will win a cake. Maybe it's the end of the day and we want to get rid of the cakes. Then you have a higher chance of winning the cakewalk. All right, now let's take a look at this one. Probability of yellow is still 2 out of 8. And then the probability of odd is 4 out of 8. But what I want you to do is I want you to notice that if I look over here, here's my yellow, 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 and then I have my odds. Odd, 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 odd. Oops. You should notice right over here that I have one where I have an odd and a yellow, which means my events are not mutually exclusive. I could land on a yellow and an odd at the same time. That means if I want to figure out the probability of yellow or odd, I cannot just add these 2 together because then I would get 6/8. But if I look at my spinner, it's not true that 6 of them would give me a prize for yellow or odd because yellow and odd are not mutually exclusive. So then what I would have to do is I'd have to look at my spinner and I could just count and I could say, okay, well, how many are going to give me a prize? This one will give me a prize, this one, and this one. So actually, oh, and this yellow one, the odds are 5/8. So whenever you see or, we can just add the 2 if they're mutually exclusive. But if there's an overlap where I could land on the example yellow and odd at the same time, I can't just add. I need to actually look at the wheel. Okay, last section is talking about compound events. So compound events are events where 2 or more things happen. So often grade 7, that's going to be with me pulling a marble out of a bag or picking up a Scrabble tile and then picking up another one or pulling another marble out of the bag. So it's 2 things happening or more, okay? Now, to keep it simple, if you want to know if an event is independent, just think independent is when I replace something. So if I'm pulling a Scrabble tile out of a bucket and then I pull another one, if I replace the first one, everything stays the same in that bucket because I've replaced the original tile that I took out. So there's still going to be the same amount of tiles. But an event is dependent if I don't replace the tile, because the amount of tiles in the bucket changes. So then my second draw, so I draw one and then I draw another one, it depends on what was taken out at the first time. Okay? So let's try that. Here we have a bag of marbles. What's the probability of green and then blue? So when you see words like then, you can think, oh, it's a compound event. Two things are happening. It's not green or blue. It's like I'm going to pull a green and then I'm going to pull a blue. So in this case, I am going to replace it. So that means it's independent. So when I'm working with compound events, I multiply. So if I look at my marbles here, let me quickly count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 marbles in total. I'm just going to write that down for myself. So the probability of green is 5 out of 12. And then because it's compound, I'm going to multiply times the probability of blue, which is 4 out of 12. Now remember, when you multiply the top and you multiply the bottom. So the chance of me getting a green and then a blue with replacement is 20 out of 144, which I could then simplify if I wanted to. Okay, so that's the probability with replacement. But now let's pretend I've green then blue with no replacement. So my green chances are still the same, 5/12, times, there's still 4 blue marbles in there, but now there's only 11 marbles left because I didn't replace the blue marble that I had originally pulled out. Okay, so this is a dependent event because the second event depends on what happened the first one. So I still get 20, but now I get 12 times 11. So I end up having 12 times 11 is 132. So you'll notice I have a better chance of pulling a green and then a blue with no replacement. So these are both compound events. This first one over here is independent and the second one is dependent. Let's try one more example. What about this one? The probability of orange or blue. So I want you to see this. Or blue right over here. Or should make me think I'm going to add. So I reach into a bag and I want an orange or a blue. So I have orange is 3 out of 12 and a blue is 4 out of 12. So in this case, I add them. It's not a compound event. I'm only pulling out one marble. So the chance of an orange or a blue is 7 out of 12. But now let's take a look at the chance of orange and then a blue. Now we have a compound event where I need to have two different things happen. It's independent because I've replaced the marble. So now I get 12 out of 144. Okay? So I could simplify that by dividing by 12, and I would get 1/12. So you'll notice the chance of me getting in one draw, an orange or a blue, is pretty high, 7 out of 12. But the chance of me getting an orange and then a blue is only going to happen 1/12 of the time. So I hope that review helps. If you have any questions on the actual review lesson today, please call me or chat with me so that I can get you ready for the test on Friday.